I think we can start now. Everybody, I think most of we have 40 participants now. So, sir, shall I start?
I think we can start.
Okay, okay. Uh, Good afternoon to all of you present here. Today, I welcome you all to the online lecture series on Earth Engage, Bridging Academia and Industry. It is the second lecture of that series. Today, we have with us the esteemed speaker, Dr. Sebastian Lobo-Guerrero. He's from Pittsburgh. So, I request Dr. Mahendra Singh, sir, to welcome our speaker.
Thank you very much. At the outset, it's my pleasure to welcome Dr. Sebastian Lobo-Guerrero. We are here at IIT Roorkee, and I'm representing the IGS Roorkee chapter. So there are more than about 50 the chapters, IGS chapters all over the India, and our chapter is very active, and it's our pleasure it's to welcome Dr. Sebastian for this talk. In fact, in this part of the country, we are very close to Himalaya. We are very close to the foothill of Himalayas, and a lot of these slope instability problems are there. So, particularly for us, your lecture will be very beneficial. So I welcome Dr. Sebastian, and also it's my pleasure to welcome all the attendees, and I believe it will be very fruitful for us. Thank you.
Thank you,
All
sir,
right,
for
excellent.
I-
Go ahead.
okay. Now I think Professor N.K. Samadia sir has also joined. So I request him to say a few words for the series and for the speaker.
Good evening here, and I also welcome you for this lecture. I am N.K. Samadhiya, and our chapter is organizing many online and offline lectures too. So we are really thankful to you that you have agreed for this lecture series, and we are waiting to hear you. And as Professor Mahendra Singh has said that we are very close to Himalaya, so we have most of the problems related to landslide and subsidence in tunnels, etc. So I hope that your lecture will be useful to us also. Thank you so much.
I would like to add here that Professor Samadhiya has been our president of the IGS, Indian Geotechnical Society. I was telling you, this is the society for which we are affiliated. He is the recent past president. Thank you.
Immediate past.
Wow.
Yeah.
Now I request V.A. Sawant sir to introduce our esteemed speaker.
Hello. So, good morning, good evening, all the participants. It is my privilege to introduce our expertise for today's lecture, Dr. Sebastian Lobo-Guerrero, PhD PE. He is a highly accomplished geotechnical engineer with 24 years of vast expertise in deep and shallow foundation design, earth returning structures, and landslide stabilization, which he is going to share with us. He served as the Geotechnical Project Manager and Laboratory Manager at AGES Incorporation in Pittsburgh, while also contributing to academia as Adjunct Professor at the University of Pittsburgh. He is a prolific author. He has published over 250 technical papers and presentations in scientific journals, geotechnical magazines, and conference proceedings worldwide. He co-authored the State of Delaware LRFD Bridge Design Manual and has served as an implementation instructor. He is leader in the field. He is former chair of the Pittsburgh ASC Geo Institute and former director of ASC Pittsburgh section. He is actively involved with the Deep Foundation Institute DFI as a member of the Anchored Earth Retention Committee and has chaired major geotechnical conferences including DFI 45 in 2020 and DFI 47 in 2022. His dedication to advancing the profession extends to his role on the board of trustees for the Academy of Geoprofessionals of ASC. He is recognized for his outstanding contributions. He has received numerous prestigious accolades, including being named as ASC Fellow in 2024, the DFI President Award in 2022, ASC Lifetime Achievement Award in 2021, and ASC Civil Engineer of the Year for the Pittsburgh section in 2020. His scholarly contributions have also been honored with distinctions such as ASC Geo Institute Distinguished Reviewer Award in 2016 and ASC Geo Institute Best Paper on Numerical Modeling in 2006. With this very brief introduction, now I invite Dr. Sebastian Logo to deliver his expertise on the topic of advanced slope stabilization by deep foundation. Thank you, sir.
Sir, before you start, I think our HOD sir has also joined. So I request our head sir to speak a few words for our speaker and the series.
Thank you, Pratik. I am very happy that you people are continuously organizing these online as well as offline courses. So this, it seems that after our IGC, which was held last year, things have things are continuing, and I think every 15 days you people are organizing these lectures. So today's lecture is by Professor Sebastian Lobo-Guerrero, who is lab manager at American Geotechnical Environmental Services. So I welcome you, Professor Sebastian, and I wish that our students, not only from IIT Roorkee but from our different parts of the country, through IGS, they will be benefited by your lecture. And I request all the persons who are listening to him to ask the questions. If you have any query, please ask, so that really there is benefit to you. Thank you very much.
Thank you, sir. Now I request our esteemed speaker, Sebastian sir, to start with the lecture. Sir, the stage is yours. Please.
All right. Well, no, thank you very much. It's a great way for me to start the day. So with all these introductions, you make me feel very appreciated and special. So that's great. It's truly an honor to be here talking to you today and presenting on this. So I'm gonna start by sharing my screen. Please let me know when you see the entire thing. So you should be seeing my entire screen, right?
Yes.
All
Yes, sir.
right. So don't worry. This is Spanish. I'm aware that it's Spanish, but I always like to show the first slide in Spanish to never forget where I'm from and never forget who I am. So my life started in Colombia. I'm originally from Bogota in Colombia, in South America. I grew up there, studied civil engineering, and then moved to, have the possibility to come to the United States and the University of Pittsburgh to do a master's and PhD. I completed those about 20 years ago. And after that, I started working in this company that we mentioned before, American Geotechnical and Environmental Services, where I have specialized in transportation geotechniques. So it's basically foundations, air retaining structures, night-place stabilization. Also, I also work in different professional societies like ASCE, DFI, and I also have the honor to teach at the University of Pittsburgh. I love this series that we're doing, or that you guys are doing, because the whole idea is to reach, academia and practice, and I think it's a great initiative. I'm also honored. I saw the entire roster of speakers that you're going to have in the series, and I'm honored to be part of them. Passing into the topic of today, I have to explain a little bit about myself too, so I don't come across as a very strange and crazy person. And keep in mind, this presentation is going to be like high energy. And I know for you guys it's the evening on a Friday, but for me it's the morning on a Friday. So I need to be high energy for the rest of the day. So my life started really surrounded by slope stability and geotech and civil engineering. My dad is a contractor of, or used to work as a contractor in Colombia for highway construction. My grandfather was also a civil engineer. When I was growing up, I assumed everyone in the world was a civil engineer. And I look at our profession with a lot of prestige. The picture that you see on the right is me at an age of like 8 or something like that. And basically, this is what I did when I was a kid. I walk slopes and I walk, landslides with my dad. And I used to take pictures and try to understand the dynamics behind. Obviously, I have no idea, the mechanics. That I didn't even know that it was a science, that geotechnical engineering existed and things like that. This is another picture on the top left. As a teenager, still with friends going and camping, but still that fascination to always go and look at, failure planes and deep angles on bedrock and things like that. And then this other picture at the bottom is 2003, so 22 years ago. This was the first presentation that I did internationally. That was at MIT in Boston, and obviously it's a significantly younger version of myself, but it was really the beginning of these presentations and everything. And I always like to remember that moment. It's also MIT in Boston, which is where Carl Terzaghi started in the US. So I'm not comparing myself to him. I would never do that, but it's just to have that in common. So, okay, so let's talk about the outline for today. We're talking about traditional methods of landslide stabilization. Our objective is to talk about slope stabilization with the foundations, but it's important to have a refresher of general traditional methods. Then we're going to go into the deep foundation part. We're going to work with 2 case studies that are going to serve really as the illustration and examples for what we're trying to do. So the same way that I start my slope stability class at the University of Pittsburgh, before we start going into very technical aspects, it's important to remember what is slope stabilization. So what's a landslide? A landslide is a mass of earth that came down, that lost stability, right? How that happened? Most of the time you have that mass. The number one cause is that you have a high water table. When the water table went up because of rain or different causes, it's going to reduce the effective stresses. Effective stresses reduce, shear strength reduces, and then it fails. There is other causes that can trigger these instabilities, as for example, overloading the top, putting too much weight on the top, or undermining the toe, right? Human activity can go and remove the toe, or even just a stream can go and scour the toe and things fail. Once the failure happens, we need to go into a process of about 4 steps of seeing what is the optimal solution. Something that I criticize many times is that in many slope stability, people start just putting things in programs and computers without really going through the proper thought of what is the most efficient, cost-effective technique. So the first technique that I want to talk today, let's say method 1, is simply remove the mass and move on. Now, that works in a few cases. For example, the case on the right, this is in the state of Ohio, where I was working in a stabilization for the installation of a gas pipe. I mean, basically, like in the state of Ohio, there is a lot of, let's say, they explode a lot of gas in bedrock, and then it's used for energy. So as they install the pipeline, sometimes some of these landslides occur. Where I'm standing on the top right side is the place after the slide. You can see that I have mud almost up to my knees. In that case, the solution was simply to remove the mass, grade these, put some kind of terraces, and put drainage. This is a problem that I resolved with 0 computations, absolutely no design, just common sense. Now, that is a very unique case, right? And it not always is effective. Why? In this case, the top of rock was relatively shallow. So by taking this out, it was no problem to just expose the rock that was behind, and it was okay. If you don't have rock right behind, you have to be aware that if you remove this mass, whatever is behind is going to fail, right? So you have to always keep that in mind. Right. Then that technique could also not work if what you have on top is critical infrastructure and you simply cannot afford, to get this out. So, all right. So then if technique 1 works, you should always go with technique 1, remove it. If because of the reasons that we discussed, such as you need to have the right of way here, you need to have what is there, if that doesn't work, then you have to go to solution number 2, which is what I have on the left. It's partially removing, similar to what we have on option 1 on the right, but in this case, I'm doing a fill. So I can do a geosynthetic reinforced soil slope, for example. In this case, what we did is we excavated the landslide out, and then we reconstructed with GRS, right? Geosynthetic reinforced soil. You can also do this with a rock fill. This case is similar to 1, but I need to reestablish what was there. I mean, I could just remove this and move away, but I have a highway on top. So that's the reason that I need to do that. So that will be my option number 2. These are more examples of option 1 here, where I'm just removing the mass and putting drainage, stabilization with lime, but it's general number 1. So if number 1 or number 2 doesn't work, then you have to jump to number 3. So what will be an option that number 2 doesn't work? That I can simply not remove what is there. So let me go back to this slide. In this case, the landslide occurred, I remove and I fill back with the GRS. In this case, on the right of the screen, I cannot do that. I have a road that is open and it has to remain open. So in this case, what we do is anchors. Ground anchors is basically the foundation elements that come almost horizontal and are just tying these back. Part of what you're going to see in the presentation, as I said, I'm very proud of what I do and I identified with civil engineering and geotech engineering. And I always like to be on the pictures, which is great. And I encourage people to do that because we need to be proud of what we do. The only downside is that I appear on every single picture. So as you can see here, it's like me through years. So if you get a little annoyed by that you see me on every picture, no worries. I'm sure it's gonna become normal as the presentation goes. Something that is added that is interesting also to me is that you can see the dates in some of these pictures. You can see how the technology evolves, but you can also see how the engineer gets older and older and older. So I don't know. I think those are like just fun things that also happen. But anyway, going back into the technical part, this is option number 3. This is anchors. If I need to establish the road again, I cannot remove the mass. I cannot do anything like this. Anchors become a really good option. So that will be your number 3. I'm also going, the cheapest solution is number 1. And as I keep going, it's becoming more and more expensive. What is the problem with anchors? If I have utilities behind this road, if I don't know the land or the owner doesn't own the land behind the road, these anchors could be anywhere to 40 feet, 15 meters, things like that. Then that could be an issue, right? So if anchor doesn't work, then what do? And that's where we arrive into other things. Okay, but before I go into the next technique, this is more about anchors. We can install them there here. One of the positives that you have with anchors is that you can test them. One clarification that I need to do on this one is you see a lot of people around on this. Actually, all of them at some point were my students at the University of Pittsburgh. Then after they finished their studies, they came and work at the company that I work. I'm a true believer that if you are planning to do a really good geotechnical engineer, you have to cover 3 main aspects. First one, you have to be really good in class. You need to be really good on theory. You need to read a lot of papers. You need to watch to a lot of these lectures. You need to be concerned about learning the theory, right? The second aspect, you have to spend a lot of time in the lab. If you really want to understand how soil and rock behaves, you need to play with that. You need to spend time on the lab. You need to do tests. You need to understand and drain shear strain by doing it, by doing triaxials, by doing direct shear stairs, by doing consolidations. And then the third thing that is extremely important is to be involved on the field. If you're going to be a good designer, you need to understand how things are constructed. And if you're going to work in construction, similarly, you need to know how things are done in design, right? So as a result of that, I take a lot of people to the field. And what you're going to see on the presentations with all these pictures, it's a lot of students and a lot of peers and people that I work with. It doesn't necessarily mean that for these construction techniques, you need that many people around. But it's just a parenthesis that I like to do. And also part of these presentations, when I look back to these pictures, is very enjoyable because many of these, they were, I can see how they were young at that point, and now they have been with us for many years, and I have seen their careers. So, okay, little parenthesis, we are still on option 3, installing anchors is very good. You can test them as shown on the pictures on the right. It brings a lot of confidence on what you're doing. This is a final product of an anchor project. That's my son, who is my companion of projects. Same way that my dad used to take me to projects, as I showed at the beginning. I try to take my son to projects so he also sees the beautiful world of civil engineering. These solutions are really practical. You install these anchors, you put a steel mesh. It could be a Macaferri mesh. It could be a geobrock mesh. It could be any of these fabulous techniques that we have. And then after a few weeks, vegetation grows and this slide is completely stabilized, right? So what we are going to talk today is not of the first 3. I just do that as an introduction. I actually have a separate presentation for each one of those techniques. It's not the topic of today, but it could be the topic in the future for something else. We can do one about anchors. We can do one about, GRS design, things like that. But what I want to talk to you today is what do you do when none of the other options work? And this is kind of a relatively new topic in the sense that the other 3 are absolutely developed already. When I went through academia, when I went to my degrees, I took classes in these techniques. After that, I also took classes with Federal Highway Administration on how to design these systems. But my point goes that we have today, we have design manuals, we have software, we have things that already deals with this. What I'm going to talk today, which is slope stabilization with the foundations, we don't have any of that. This is a technique that started probably as old as humankind have been around. If you have a slide, you just put like a post trying to stop it. But the understanding, the engineer understanding of that really didn't start until very recently. When I was doing my PhD, I remember reading about some techniques that were trying to use elasticity. Unfortunately, something like elasticity has nothing to do here. This is a lot far more complex, and it's a lot of plasticity here. So this topic really started getting a lot of attention in about the year 2005, about 20 years ago. Eric Loer at the University of Missouri in Roland, he started looking into this and trying to identify what were the main things. It was around the same time that I started getting very involved with ASE and the Foundation Institute, and we started also doing research on this. So the initial failure mechanisms, basically, or what we want to understand here is how does this fail? What, if I have this rock failing or this mass failing, what can I have? So I'm going to have some passive pressure in front of this, right? We're going to have some kind of resistance, but how much is that passive pressure really working? I mean, that will be Coulomb or Rankine. How much is really working if I have a failure plane below? I'm going to embed my piles, right? These are discrete elements. These are piles that are going into the thing. It's not a continuous wall. It's just separate elements. How much do I need to space them, right? How much I need to embed them into the competent strata below the failure plane? How much I need to space them? What is the structural capacity? So as a result of different research that we were doing with DFI and AEC, we arrived to the following conclusion. The soil above the failure plane possibly fails in passive pressure, which is okay. It's going to give you a very limited resistance, but that's okay. The structural element is the one that is going to really take the load. And the structural element is going to go on bending. So bending will be like this, right? Bending will induce tensile and compression stresses. And it also works in shear. So shear will be pure shear, not much bending, but just a pure shear. Then because the piles are spaced, there is going to be some arching. So we go into this magic number of 3 times diameter. It's a number that we learn in foundations as the minimum separation between piles. We know that if we put them closer than 3 times diameter, we have overlapping effect for the stresses. So we want to keep them at least 3 times diameter. We also see this on tunnel design, right? When you have a cavity in a semi-elastic space, you need to have another one 3 times diameter or more so they don't interfere with each other. And what is going to be below the failure plane is going to be passive resistance in the way of Rankine or Coulomb, and that's what is going to help us passing the forces from the structural element into the ground. So this is like the framework, this basic design principle of what we're going to do. So let's go into case studies and practical examples to understand how we do it. So this is a slide that occurred in the city of Altoona in the state of Pennsylvania in the US, where a block of rock start moving. So it's what you see here on the right. This is at the beginning of the project. This block start mobilizing and it starts coming down. It's a risk because you have a road that passes below. You have a traffic line, electric line that is right next to the slope. You have a gas line that is under the road next to it, and you have a shopping mall. So if this comes down, it's catastrophic consequences. So we were called to the project. We went there. We started analyzing. Of course, I'm never shy from a cool picture, especially when I can share it with the engineers that I work. So initially, it was the 2 of us doing a site recon and understanding the project. But then things start turning bad pretty quick. This is the next day when we woke up. I was looking on the news. Obviously, the local news have a picture of this, and it has this bar saying 2 others after warrant served this morning. And I was like, man, is that us? Are we getting into trouble with the law? At the end, it didn't have anything to do with us. It was just news for the day for other topic. But something that was interesting was seeing that the news were covering this, and they were showing these shots. Initially on the project, we have a drone. We took the first day. As soon as it took off, the wind took it and crashed it against this, and we lost the drone. So for the remaining of the project, we did not have a drone. So we end up actually using the pictures from the media to understand better the slide. What I like to point out here is you can see the crack that is going here, and it's kind of delineating the size of this slide, right? These are more pictures from the same newscast. You can see in better resolution and better detail the crack. It's the one that we were taking the pictures below. But something else started appearing interesting at this point, which is there is a channel on top. And channels are good. Ditches are really good on slopes to take the water out. But every time that you see a tree, it's a bad sign. Because if you see a tree in the ditch, these ditches are supposed to be impervious to water. And anything that you have a tree on, the tree is going to end up finding a way to penetrate and pass with the roots. So when you see a tree on a ditch, that means water is leaking. This is another picture from the top. Now you can see that ditch. You can see those trees. So obviously, the moment that we walk, we could hear water coming into these cracks. So with discontinuing that, we basically recommended the installation of this pipe. And now the water is being conducted to avoid any additional infiltration. So the findings of the reconnaissance were this is sandstone interbedded with shale. The failure is really occurring on shale. It's a deep angle of 16 degrees. That is a very, very, let's say, a small deep angle, right, for a typical slide. I always say that I'm never really that concerned with the slopes that have a high deep angle, because that means there is probably a shallow failure. As the failure surface plane start becoming flatter and flatter, you need to get really worried, because that means it's probably a huge mass coming down. Also, when you have something that is steep, you have good friction angles. So otherwise, it would not have existed before. But anyway, so we have that. We have the wetlands above the area with the ditch on top, and we have the trees, and then obviously the water being the running case. The slide plane was the weather shale. The block was about 46 meters upslope, 122 meters wide, and about 6 meters thick. So it's basically this chunk coming down. More pictures as we continue investigating the project. One of the rarities that you have in a project like this is that this is moving so fast that you can enter the tension crack on the back, and you can actually see the failure plane being exposed. And you can actually sample this and conduct laboratory testing on the failure plane material. It's very unique, because in most landslide, you have to do shade diffuser. You have to do something to get a sample of the failure plane. And it's never going to be as undisturbed as in this case. So I'm just going to take a second to talk about the role of the media, because I think it's something important, and it's definitely something that I don't think in academia we talk enough. The media seems to be seen as a negative thing, and in many cases it's a negative thing. I have also done my career doing some forensic investigations where the media has not helped at all. But the media also have positive things, right? Like as what I was talking at the beginning, we have some of those drone images thanks to the media that we could not have had to understand the problem. But some of the negatives also to be shared. These are some of the highlights that they were publishing during those days. They were talking an expanding fault in central Pennsylvania. There is not faults in central Pennsylvania like that, especially not at this location. They were talking about the hillside was going to break apart, a lot of panic and speculation. The whole area was going to be electrified, which is not. I mean, the power line was cut immediately, right? The power was, completely stopped on that area as soon as this was identified. This is probably really dangerous too when the media started speculating on the causes. So they were saying that it was caused by cutting too far in the hill. This shopping mall and this construction happened about 10 years before this failure. So, I don't think one is related to the other one that directly. But then one of the ones that caught my attention too was saying that police were concerned, and there were a lot of Facebook activity also in the area that is parked. Seeing the pictures that you saw before, knowing the person that I am, I was not going to be out Facebook by anyone. And I was like, if anyone is going to have a cool shot on this project, it's going to be me. So I went the next day after seeing that, and I took this picture. The engineer that was working with me, it's a good friend. Poor guy had to spend like an hour taking the best shot and all that. And I really like that shot because, you can see the crack on the side, and I think it's very impressive. So many people say that it's not safe. It was safe. I don't do anything that is not safe. I took all the precautions. But anyway, beyond the cool picture, this picture also have a meaning, which is the subsurface investigation. Ideally, in a project like this, you want to have a comprehensive subsurface investigation. You want to have borings. Typically in things like this, I like to install inclinometers, right? I like to install extensometer, piezometers. Instrumentation is really important to understand things. But in this case, this was happening so fast, I was not going to have the time. The block that is on my right was moving. You could see every time that I went to the project, it was different. So I was never going to get a track rig that was going to come on this side and do a boring or install an inclinometer. I could have some on this side, but I didn't even know if it was moving or not. So sometimes you have to go back to basics and really where everything started for us. I'm a big fan of the free body diagram or basic physics fundamentals. So I also love numerical modeling, but it's important to understand the fundamentals to then move into the next step. So in this particular case, since I could not do any instrumentation or monitoring, what I recommended was let's just go back, put some nails, put some kind of monuments that we can actually just follow with general surveying, right? So that's what we did. We installed some points here with big nails, and then we just did surveying every day on those. And what we established is that this was moving about 5 centimeters a day. This part here, the right side. So the right block is moving 5 centimeters a day, but the positive news is that the left part is not moving at all. So that's when you start going through the different scenarios. Scenario number one, can I remove this and live with this? So let's do the test on this one. Can I just remove this and go? Technically, I could, but I don't know if this is going to stay. I know right now it's not moving, but that doesn't mean that in the future it will not. So that option probably is not exactly ideal in this case. Option number two, can I remove this and put like a geosynthetic rock, a geosynthetic soil, a geosynthetic reinforced soil slope, or can I put some kind of rock fill? Definitely an option. And we analyzed it, but the problem was to contain what is on the left, the size of that rock fill and GRS was going to encroach into the road. So therefore, that option was not a solution. So I'm running out of ideas. Then option number three, can I come and put anchors? I can't. I mean, how can I get a rig into this, right? So when nothing works, that's when this option comes. So I was like, this is the perfect case for slope stabilization with deep foundations, because what I do is I come and put my vertical piles here. That's going to retain what is on the left. And then I can remove this in a slow manner and a safe manner. So it ended up being the concept that I have called here as the Taylor plane. Is basically going and putting 3 rows of piles. This is going to take care of stabilizing the upper part. And yeah, and then that's pretty much it. Give me 1 second. Let me adjust. I have the sun is coming out in Pittsburgh and it's really hitting my eyes. Okay. So this is the solution. We start working on it. As we were removing this, I was always in constant talk with the contractor, and I was telling them we need to go there. We need to excavate down to the failure plane. We take out the failure block, and then at the same time, I'm going to design these elements to stabilize what is above. At the beginning of the project, there is always a lot of stress. The contractor, the operator, was very professional. He was, we were communicating, but it was basically all work related, right? So he was excavating. I was verifying that we have the failure plane exposed, and we continue. When we advanced further into this, one day he asked me and said, "Can I ask you a question?" And I said, "Yeah, absolutely." He said, what is the importance of the Taylor plane? So, Donald Taylor is one of the pioneers in geotechnical engineering. One of the hobbies that I have beyond the technical aspects of geotech engineering is I love looking and collecting classics books for geotechnical engineering, especially the pioneers of what we do. So with time, I end up having a copy of Terzaghi, Theoretical Soil Mechanics, Terzaghi, Soil Mechanics in Engineering Practice. I also have, for example, Peck and Hansen Original Edition. So I love these old books, and one of those that I have in my collection is Taylor's book. It's one of the first books on geotech engineering, and it's one of the first books that talk about slope stability with the charts, Taylor charts. So the fact that this operator was asking me about this, I was like, this guy knows it all. He knows how to operate equipment, he knows how to do the construction, and he also knows the theory. Then we start talking, and I realized he really was not referring to anything related to Taylor. What he was trying to ask me was the relevance of going to the failure plane. And I realized that it was my mispronunciation of English, that when I was saying failure plane, in his ears, he was understanding Taylor plane. So it was a fun anecdote. We have fun. It took a lot of the stress out on the project. As a result, I end up calling this stabilization the Taylor plane method. Funny part is I end up doing this report, and this report ended up going to DEP and many reviewers and agencies. By that time, it was too late to remove the name. So that joke ended up going far. Nobody even had an idea that Taylor plane really didn't mean anything here. But anyway, that's the way that we end up stabilizing. It was basically installing these deep foundations and removing the block. We start working parallel. As we remove the block, we start designing this. Now, how do you design something like this? So the idea really came, one of the advantages of having a project, a landslide on a shopping mall, is that you have a restaurant that is right next to it. So the design of this really came on a napkin during lunchtime while I was working there, having lunch and seeing them initially remove that block or the parts that were really dangerous. I was thinking, this is nothing different than what you do in physics in high school, in statics in college, or even in solid mechanics. You have a summatory of forces on an inclined plane. You have a sliding block in an inclined plane. You do summatory of forces perpendicular to the plane and parallel to the plane, right? So what is your resistant force? You have the weight by the cosine of the angle. It's going to give you the normal. Normal times tangent phi is going to give you the shear force going up, and your driving force is the weight and the sine of the slope. So you can do this. So I'm sure everyone did it in high school and also in college in the statics. You can do this and you realize what is the force that I'm missing to get a factor of safety 1.5, right? So that's pretty much what I did on that napkin, and I find out what is that force. That is called the unbalanced force. How much do I need to increase the shear, right? Like the summatory of forces on the shear plane to get a factor of safety of 1.5. Factor of safety being the forces that I have, the resistant forces, divided by the driving forces. So I did that, calculate that force, and then I can simply take that force and calculate how many bars I need or how many elements I need into the page to what spacing to provide that force. What is the resistance of a bar? This is pure shear. This is a block sliding on top of a rock, right? That's pure shear. And the shear of steel, we know it because based on the Moore Coulomb and a horizontal failure envelope on top, is 0.5 times the yield times the area. So if I know the resistance of 1 bar, and I apply a factor of safety to that too, obviously. So if I know the resistance of 1 bar, I can calculate the number of bars and the spacing. So that's the way that I did it right there. And I found my solution. Obviously, you start with something like that, then you go to the office and you refine it. I end up running a slide, rock science slide in 2D to prove it, but I basically got the same answer, right? So that's the way that it was done. Obviously, the friction angle came from the lab testing that we did, the fact that we were able to, to go and do that. So I did one check for a factor of safety of 1.5 on original design, and I also did a residual case. Obviously, a material like this is going to have, it's going to have peak strength when the rock is not weathered. Then it's going to have the fully softened, friction angle, which is going to be once the rock weathers. And then from fully softened, you go down to residual. This is what Skempton was saying. Tim Stark at the University of Illinois has studied comprehensive in fully softened, but that's pretty much understanding. The rock is going to be intact. Then it's going to have fully softened strength, then which is going to be kind of like a peak of when it became soil, and then goes down to residual. So we also did a residual case, which is basically once it has moved for a long time, and we want to increase. How do I know the residual friction angle? Two easy ways to do it. One, with the same test that we have, obviously you run it to a significant deformation. And then the second one is you can just back calculate it. This is today, or at that point, it was still there. So the block is moving. I know the deep angle. If I want to have a factor of safety of 1, it means that the friction angle of the interface is exactly the same as the deep angle of the rock, right? Factor of safety of 1, basically. I don't have any other forces. It's just the driving force of the block, and the resistance is the pure shear. So when you do the math, you end up finding that is the infinite slope. Your factor of safety of 1 means your friction angle is the same as the inclination. So once I know that residual friction angle, I just put the bars to see how it increases with that residual friction angle, and I get a factor of safety of 1, 2. Typically, we look for a residual extreme case factor of safety of 1.1. So once I have this, now I know I have the bars that I need to stabilize this. I need to, do the calculation on the structural aspect, which is what I said is just the yield. You apply a factor of safety on that, and that takes us to the specific bars that we end up using. A number 20 bar, 517 megapascals, 9.1 meters. We end up doing to install it as a micropile, so it's a whole diameter of 152 millimeters, 15 centimeters, basically, with a 21 megapascal concrete. I did not use the strength of the concrete for anything, right? It's just the steel, but obviously to install the steel, I need to make a hole, and I need to backfill that hole. And at the end, we end up doing 3 rows. Spacing into the page is 8 feet or 2.4 meters along the row. Then what happened with the bar? The bar takes all the load, but it has to pass it to the ground. So for below the failure plane, I assume that I have passive pressure. You can calculate it with Rankine, you can calculate it with Coulomb, and I use a factor of safety of 2 to make sure that I have enough embedment to contain the force that is being taken by the bar. This is a plan of the, of the final solution. We have the 3 rows in the critical area, 2 rows, and then it disappears into 1 row. The toe of the slope is here. This is the scarp. A total of 110 micropiles were used on this. And then this is the installation of the first micropile. I highly encourage people to always celebrate the profession, celebrate the design, celebrate the efforts that we put by doing this, right? Take a picture with the first element being constructed. So this is the first micropile being installed. It's a solid bar, solid steel bar. As I mentioned, number 20 is green because it has epoxy. It's epoxy coated because of corrosion. The fact that we have water running in this area through the cracks and all that, it was a concern. I don't want these bars to erode with time, to corrode with time. So that's the reason that we put the epoxy coated. You can see more bars here on the right side. And then these little white things that you see are just centralizers. That just makes sure that as the bar goes down, it remains in the center. And this is the tremie grout. This basically this yellow pipe goes here and is what puts basically the grout. It's just cement and water, but basically that gives the strength. And then when you look the picture, every white dot that you see into the page, it's a location for one of the bars. Now, at the beginning of the presentation, I was talking about a spacing of 3 times diameter. That happens when you need arching, when you are in soil and you need the stresses to concentrate in a point. The fact that this is bedrock, it's a block. It's one body, so it doesn't have to be 3 times diameter. You can be a lot more because there is no fractures between that rock. So, it's just going to behave as a block. So in this case, the spacing is a lot more than 3 times diameter. This is more pictures, construction of the second and third row. At this point, production is going fast. You can see how the excavator basically takes the bar and lower it. This is a Casa Grande rig that is just installing it. And these are some of the bars ready to be installed. Job continue, and this is the final product. Our profession sometimes is a little ungrateful in the sense that all the effort that we put and all the great construction that we do end up being buried in the ground. As a matter of fact, a company, Keller, used to have a slogan that says, "You will never see our best work," meaning that you will never see our best work because it's buried. I guess that was taken out because it also kind of keeps an idea that we're not really putting in a good effort, so they don't use that anymore. But it's just true. I mean, look, this is the picture of the completed project. When we finished, it was already winter, but you can tell all that block that was really scary looking is gone. We removed that. And then we installed those 110 micropiles here. You cannot even see them because we reconstructed the channel and the ditch, removed the trees, and it has a geosynthetic clay liner, and everything is gone. So it really it blends in with with nature. I have continued to work with the owner on this project. I mean, this project was completed about 9 years ago. We go once a year, we monitor, we make sure everything is still in place. So far, after 9 years, it has performed with absolutely no issues. So it has been very successful, and that's the reason that I like to show it. I also have done other stabilization like this on rock, but this was really graphic, and that's the reason that I like to. I think it illustrates the main point. I'm a true believer of publishing your case studies and sharing everything with everyone. At the beginning of my career, I used to publish a lot on journals that you have to pay subscription, but I don't like that really, because then it's not free access. And I think if you write something, it should be for free access. So I publish a lot on the Deep Foundation magazine. It's free online. Here is the link of the presentation. If we are not connected on LinkedIn, I highly encourage that we get connected on LinkedIn. I look at all my messages on LinkedIn. I reply to every single one. If you need a copy of the paper, I'll be happy to pass you the link. But even if you don't interact with me on LinkedIn, it's extremely important. The first homework that I do on my classes here at the University of Pittsburgh is for a student to open a LinkedIn account. It's the way that you find jobs, is the way that you connect with the industry. But anyway, so this step-by-step procedure, I put it on this paper, and since then this paper became kind of like a reference for other people trying to do this slope stabilization. But now let's go into another case, which is the end of the presentation. Let's go into the soil case. Let's see what happened when you don't have rock. How do you do this technology? So for this particular one, it's a little more complicated on the way that the project went. So I'm going to start with the end product, and then I'm going to go back on time of what was the condition when I started. The end product, as this is also in the state of Ohio, they were doing what is called a Rex booster station, which is shown on the top left. This is basically a project of putting some machines and some equipment that take gas, that is natural gas, that is being pumped, and basically increase the energy so it can continue to go on the same pipe and advance more and more kilometers. So to do that, they need to have a very specific height where this is done. In this particular project, this embankment here did not exist. What is on the left, this used to be an old slide. To do that, they went there, they excavated down to bedrock and put this embankment into bedrock. It was very concerning for them because on the right side, this is a hill that continues going, that is an ancient landslide. So they said, we want nothing to do with that old landslide. We're just going to excavate down. We're going to put this on bedrock. And that's what they did. I was not involved on that part of the project. I have nothing to do with that until that point. Once they finished, they realized they needed to put a pipe on the toe. But the problem is, to do that, they needed to construct this berm that is here on the right side. And to do that berm, that's new material. That berm is so they can run the equipment to install the pipe. And by putting this weight, you start what is called a progressive failure. You put this here, you destabilize this goes down. Once that goes down, the new embankment goes down, and everything that you see is going to fail. So they needed to be able to construct this in a safe manner. The designer for this project, for the one on the left, did not want it to be part of that. They say, no, I finished my job. You guys constructed the embankment. My work here is done. That's when they contact me, and I have no idea that the original designers say no. So sometimes you jump into these projects without really having the full information. But anyway, once I look, I say, no, I mean, this is a lot of load that you're going to put. There is that existing landslide. You have to do something here. So that's the idea that came, can we reinforce this to protect this slope and do this berm? So now let me jump into what I saw the first time that I went. So when I went there, this was just finishly constructed. They have the embankment there. Vegetation was only starting to grow, as you can see on the picture. There were nothing obviously under there. It's just like a ravine, and this keeps going down. So, you know, what I look initially, based on what they passed me from the previous report, it was that it was a colluvial soil, right? Shale was the bedrock, and then the rock was about 5 and 9 feet. So it's relatively shallow bedrock, but there is a lot of unstable material here. So because the previous engineer walked away from the job, and this is an advice for your practice, if you jump into a project that is kind of halfway, you always have to doubt things, right? If I'm taking the logs and the records from an engineer that is no longer associated with the project, that doesn't make me feel very safe. So in this particular case, I recommended that we develop our own our own investigation to confirm conditions. So that's what we did, and we compared, and I actually ended up matching very well the one that was done before, but I needed to have that. So okay, so what we know is that it's an embankment 33 feet. That's what you see on the left, supported on bedrock and need the pipeline at the toe. This is just a schematic of basically what they wanted to construct. Is just this little berm to be able to install the pipe. It's 15 meters wide and it's about 14 meters tall with a 1.3 horizontal, 1 vertical. So again, the concern is if you construct this thing in red, this fails. And once this fails, what is above fails, right? And then you have progressive failure going on. So solution was very similar, going into 3 elements, right? 3 elements to stabilize this. What this will provide is that if I have a failure circle like this is going to provide some unbalanced force of shear resistance. It's going to provide, and then that's it. Now, the previous case, I was using micropiles because of the scale. I cannot use micropiles here because they literally are too small to the scale. So now I have to upgrade into drill shafts, right? I need elements that are bigger. So that's pretty much what it is. Here is the existing slope. I'm putting this tree. I'm doing this berm. This should take care of those circles. This is the analysis. This one is too complex to do on a napkin, so I went straight into slide 2D. This is the case if you put that berm and if you put this here, what happened is your factor of safety needs to decrease, and it's extremely important to define what is failure or not. Many people tend to see failure as a factor of safety less than 1. Your driving forces are more than resistant forces. That is the common sense definition of failure. But look at from the point of view of the owner. For the owner, failure is when the factor of safety is not what they want it to be. If it goes below that, that's a failure, right? So in this case, when you put the weight, when you put all these, your factor of safety reduces. And once it reduces, that's not what the owner has. This is critical infrastructure. So to avoid that, we come here and we put these 3 elements. And when we put the 3 elements, now you can see when the circle comes through, the factor of safety increases to 1.5. This is the factor of safety that you want there. You want to have this at 1.5. You don't want to risk what is there. Now, Slide, and I do a lot of things with rock science and Slide. I teach classes with them. So I don't want to be seen as I'm favoring one program. There is plenty of programs out there. Slide is what I use, but there is plenty of other programs that are equal on the quality, and you can do it on this. These programs now have the option that you can put an element, a vertical element, and you can just say what is the force that that element provides horizontally, so it will increase the factor of safety. So you can, that unbalanced force that I start talking at the beginning, you can put that on the program. You can say, I assume 100 kips or whatever, and the program takes the circle, when it intercepts, put a horizontal force of 100 kips per pile, right? And you put the spacing into the page, and it calculates the new factor of safety. So that's the way that it was done. We do this, we find out what force do I need per pile, right? And once I have that, I can continue with my design. In the previous example, it was easy because it was pure shear. So I can say, okay, if I know the force that I need on that element, I can calculate the shear capacity, 0.5 times yield times area, and my problem is solved. The problem here is that it's not that simple. I know the force on the pile, but that pile is not working on pure shear. Now I have more like a pressure that comes like in a triangular manner because it's soil. It's not just at one plane. It's a cumulative force. So one of the big advantages or the biggest steps that we had with this, and this comes from Eric Loer, is to use LPile. So LPile, it's a program. There is other programs. LPile is developed by ENSO, but there is other programs like RSPile, for example, that you can use that based on PY curves. Basically, a PY curve is just having a pile and putting like springs in front of it, and you know the constant of that spring. So as it moves, you know how much force is opposing. So if you do a program like this, you can know based on the formation how much resistance you have. The traditional way to use LPile is that you calculate deflection. You give me a pile, you give me a vertical load, you give me a horizontal load and a moment, and I calculate the deflection. The original aspect of what I'm gonna show now is for this application of landslide stabilization, we do it the opposite way. I assume a deformation, let's say 1 inch, all the way from the top to the failure plane, and then the program gives me back what is the force that I have on this pile, what is the shear that I have at the failure plane that makes this to happen. And when I know that, I can just iterate between a slide and LPile and see what element do I need. It's extremely convenient because now on LPile, I put my steel section. If I'm doing a drill shaft, I can put the reinforcement cage, or I can put the H-pile or whatever steel I put inside, and the program is going to tell me how much is the resistance, right? I put the deformation, I have the element, it gives me if my factors of safety are okay for bending and shear. So that's the way that we run it. This is the output from the program. So I said, I input the steel section. The program calculates, it forces the deflection. Based on that, it gives me the shear force. It gives me the moment. And then I can put the steel section and make sure that I have enough, right? If I put my steel section and I know what is my maximum moment and all that, I can calculate all this and I can see if I have a factor of safety. So I recommend typically using 1.5 for structural elements. So you have your global factor of safety for the slope stability, and then you have your individual factors of safety for like the structural aspect. So we check shear, we check bending. In this particular case, bending controls by far. So even though you're checking shear, bending is really the one that controls. So that's one of the lessons. In bedrock, when you have block on block, it's pure shear. In soil, it's really bending what controls. That takes us to now, like, the final detailing of the solution. So we use drill shafts 2.5 feet in diameter, spacing 3 times diameter, because I need that arching to happen. Between rows, we actually space them at 6 times diameter because I want arching to occur within the row. I don't want any effect between the separate rows. So typically 6 times diameter is that number. Then, the steel section, it's a W460 by 158, 345 megapascal steel. And then the length of this was 12 meters, 21 megapascal concrete. This is a picture with the last element. So as I mentioned before, I tend to take the picture with the first element of the foundation. In this particular case, I took with the last element of the foundation being constructed. And that takes us to this picture, which is really going back in full circle. So this is the end. This is when we are putting this pipe. The whole thing, this project was for this moment. It's basically, we have 75 drill shafts that are buried under this embankment here, that the whole point to do it was to guarantee the stability of this, right? That when they make this excavation, none of these fails, that when they put this load, none of these fails. And there is a big level of satisfaction, and the smile that I have there means a world, because everything we do, everything that we prepare, I show a picture of me at the beginning of the presentation when I was a kid. Everything that I have done since that day is to learn every day and to become better and better and learn more geotech for moments like this picture. This is a whole life and a whole career to have a smile saying, I know how to do this and I stand behind my work, right? I have no concern that this is going to fail. This is what I do, right? And I think that's something that if you don't remember anything from this presentation today on the technical aspect, I'm okay with that. As long as you remember what I'm trying to say right now. Everything that you're dedicating your life to, that you have put your efforts, is worth it. And you need to enjoy the moments when you see the success for that, because you don't have, that's what I mentioned at the beginning. Civil engineering for me is not just a job. It's a whole thing. It's a profession. It's a prestige, right? So it's important to understand that what you are studying right now, this is not the job between 8 to 5 that you're going to do. This is a way of life that you chose. So moments like these are important to remember. Similar to what I did on the other one, I wrote a paper step by step. It tells you how to calculate that. That also became a reference for people designing these kind of stabilizations. And that doesn't stop there. After that, I keep working on the subject. This is other examples of, another example of stabilizing a slide with drill shafts. You can see like where we're putting this. It doesn't really end up also the theory. I continue to evolve the concepts that I was explaining before. For example, one of the things, and it was done in this project, you can see the piles already constructed. These days, I'm connecting elements. The previous examples that I show you, these are separate individual elements. Now I connect this with a beam, right? There is a lot of advantages of connecting: redistribution of stresses, redundancy. If you run it with final element, you see that your system actually behaves better if you have. So that's something that I do now often. Another thing that I do, which is not shown on this picture, is these elements, I never put them completely vertical. I bar them slightly. So I have bending resistance, but I also have axial resistance. So, I'm currently working on projects that I'm implementing this. My hope is to this presentation modify it at some point to include these new developments. So in conclusions, this is a cost-effective solution. It's by no means is the least expensive. It's probably the opposite. It's one of the most expensive ones, but it really has a niche. It really has a space when none of the previous three methods that I was describing, when none of that works, this really becomes useful. So, it's I don't work on selling you one technology or the other one. I'm a consultant, right? I design micropiles, I design drill shafts, I stabilize landslides on every potential way that there is to stabilize. Every time that I do a presentation on a topic, I like to highlight where this becomes useful, right? So to me, this one is extremely useful, but you have to go through the thought of seeing if the previous three, removing, if that doesn't work, if a rock fill, a GRS doesn't work, if ground anchors doesn't work, you have to go the process. Something important on this, understanding that the structural design controls. Shear is what controls in rock. Bending is what controls in soil. You need to have factors of safety that are independent. From the geotech point of view, you need to analyze global stability. You need to find that unbalanced force. That's the whole point that we're doing this. And then once you have that force, you design your structural element. But from the geotech point of view, you need to make sure that you have enough embedment below the failure plane. So that's going to have a separate factors of safety. What we were talking, Rankin or Coulomb, you analyze that with an independent factor of safety. Spacing, if you are going into the row 3 times diameter, so you have the arching, but between rows 6 times diameter, so you don't have overlap of stresses between rows. And then just to conclude, I love doing these talks. A lot of these things end up on YouTube. My understanding is this is going to end up on YouTube. If you want to learn about other topics, different presentations, just look me up on YouTube. There is a lot of presentations there. If you just type my name, the list appears, and and you can see if there is something that you want to learn more. I highly recommend it to also my students if you start your practice and you want to learn more about, I don't know, micropiles, or if you want to learn more about ground anchors, active ground anchors, if you go to YouTube, you put my name, you put the name of the technology, I can guarantee you there is a video there where I explain the technology. So that being said, thank you very much for your attention. As I mentioned before, LinkedIn is a powerful tool. If you don't have an account, make sure to have an account. If you have an account, make sure that we connect. Send me a message, send me an invitation. It is truly the way, I don't know, I have a LinkedIn account for the past 17 years, and the way that has helped my career is tremendous. So I highly recommend you do the same. With that, we can pass to some questions if we have time. And thanks for your attention.
Yes, sir. We can take up few of the questions, I think. First question is, how important is it is to conduct the rainfall condition, like if slope analysis for rainfall conditions?
Yeah, so that's a great question. So the water in this case, man, now everything is dark. Let me just open this. I'm playing with the sun. The sun came out during my presentation. So yes, so the water is, oh, this is worst. Let me just go back to closing this. So the water is extremely important because as I mentioned at the beginning, having that high water table is gonna reduce stresses, right? It's gonna reduce effective stress, and it's gonna reduce the shear strength. So in both cases, I consider the water table in a high point, right? So you always have to anticipate that you're gonna have rain and you're gonna have a high groundwater table and check it, right? I typically try to go a conservative one. If I have a really true concern about it, you can always do an additional run and consider that an extreme event. So you can design for a factor of safety of 1.5 with a regular groundwater table. But if you think that it could go really high, then you say, okay, I'm going to consider that. But that's going to be an extreme case. So I can analyze it with a factor of safety of 1.1 or something, just to make sure that that is there. But yeah, I mean, water is the enemy. Taking it into a good context, water is the enemy in the sense that most slides that we see are caused by water.
Thank you, sir. I think that must have answered that question. And other question is like, is the method you told, this piling method, is can be applied equally to the large scales landslide as well?
Yeah, correct. So that's a very valid point, and I appreciate the question because it's a matter of a scale, right? So the first one that I show, I mean, it was big, but with micropiles, it was okay to do it, right? The second one, it was big too, but with drill shafts, you could do it. But I mean, more and more, we see landslides that are epic proportions, right? At some point there. So at what point these things work or not work? Let me put you an example. I look at a solution like this on a slide here in New Baltimore, and we were looking at it. And if you just try to put, I mean, if you put enough shafts, it will work. But it goes into numbers that are ridiculous, right? I mean, the shafts give you resistance. You can go to 11 diameter shafts, right? I mean, you can try to go into 4-meter shafts. But even with that, now the cost is getting ridiculous. It will work in paper. You can run an analysis and show that it worked, but it's just unconstructable. So then a lot of the time on those massive slides, my advice typically is you need to do a hybrid solution to unload and reinforce. So when you pass certain size of a landslide, you cannot just put elements trying to contain it. You have to go and excavate, unload in the sense of excavate material, let's say from the top, reduce the load, and then work with the remaining and then try to stabilize that. So that's really an art to really see the size of these massive landslides and try to partially excavate, partially stabilize. That will be my advice, because if you try to just stabilize, you can do it in paper, you can find the elements, but it will be, from the constructability point of view, it will be not feasible, and from the cost point of view, it will be insane.
I think we can take one more question, sir. How was the friction
I have
angle of the
time. I have
interface at?
time.
Okay, no problem. How was the friction angle of the interface at failure plane in the rock slide measured? Like in the first example, how was the friction angle
Mhm.
in the failure plane measured?
I love that question. Thank you. And in purpose, I try to pass fast on that when I present and see if somebody comes back and it's like, wait, come back there for a second. So, okay, so look at the information that we have, right? So you have an slope that is already failing. You have a block that is already failing, right? So if you just do a back calculation, right? A back calculation as the first thing that we learn in slope stability, you can run that and say, I have a factor of safety of 1. So I have the block coming down, I have a factor of safety of 1. As I said, if you just do the infinite slope, you end up finding factor of safety equal to 1. It's equal tangent phi divided by tangent beta, beta being the inclination. So that one gives you the friction angle of the residual state. That means the friction angle when the block has been moving for a while, right? So we know that we have friction angles that are peak when the movement starts, and as you keep moving, peak comes down into residual. Or we can call it fully softened if we are talking about rock, and then when it weathers is the fully softened angle, which will be the peak, and then weathers down and into residual. The one that I can back calculate is the residual because that's what is moving. But what I need to know too is the fully softened. How do I get the fully softened? If I go and take that sample, the way that I was mentioning it, and I just run, let's say, a direct shear, that's going to be that's going to be the residual already because that material already went a big length. So we did that. We tested that. We double check the residual. To estimate the fully softened, the only way that you can do it is trying to reproduce the history of the site. So what we did is we took material from the failure plane, we crashed it, we basically mix it, we put it at a liquid limit, right? Mix it, completely refabricate it, put it at the liquid limit, consolidate it. Once you consolidate it, then you put a direct shear. When you do that, you get an estimation of the fully softened because by mixing it again and putting some structure into it, you are basically simulating the process of that shale weathering down into clay. So we measured that, and that's the one that gave us 22 degrees, I believe. So 22 degrees was the friction angle to run the fully softened peak condition, which is it has not moved. It weathered down, but it has not moved. That's the factor of safety of 1.5. And then using the residual friction angle, we check, which was 16 degrees, we check for a factor of safety of 1.1. These values are insanely low, right? And that's part of what I love about this project. I think many times that people see this presentation, they are not used to see friction angles this low, right? When you take solid mechanics foundations, you use friction angles of 30 degrees, a clay could be 28. These shales in this part of Pennsylvania are extremely, extremely low on friction angle. They wear down in a clay that it's actually known as like in this area in Pittsburgh, it's called the Pittsburgh red bed. It's very high in iron, and we are used to see friction angles of 12 degrees, 14 degrees. It's material that is extremely soft. So this particular case was a little better. It was 16 degrees on residual, 22 degrees on fully softened. But I know it's low. It's impressive the first time you see it.
I think that must have answered the question. Last question is, sir, like if you have to choose between improving the soil strength or improving the drainage to prevent the landslide, which one you opt? So that's a question,
Yeah,
sir.
so that's an excellent question because drainage is, honestly, drainage can solve a lot of the problems that you have, right? Water is the enemy. A lot of projects that I have done have finished in just drainage, right? If it's something that has not failed, if you just start seeing signs of things, if you lower that water table, if you install sand drains, if you install ditches, you can remediate a lot. Unfortunately, most of the projects that I get involved, that point already passed. So even though we do drainage to alleviate the problem, we still need to improve conditions to contain the consequences. But if you are at a point that failure has not occurred, but you are seeing signs of things going the wrong way, drainage is the main thing. It's amazing how much just taking care of the water can save you problems in the future. And yeah, and I know it's funny because we all know the value of water. So that's the reason when I said water is the enemy, I don't really mean it in a serious way. I'm just saying taking care of the water is the not taking care of the water, it will be the enemy.
Okay, sir. Thank you. I think if the people have more queries, they can reach you out on LinkedIn or they can mail you regarding that. So
Yes, no, absolutely.
yeah.
Absolutely.
So
As I said, I read every single comment. Sometimes it takes time because sometimes it's a lot, but I can guarantee you I'll review your comment, I'll review your question, I'll answer it with time. Just shoot me a direct message on LinkedIn.
okay, sir, your lecture was very informative. Now we have come to the end of the lecture. Now I request Professor Mahendra Singh sir to present a vote of thanks.
Uh, I thank Dr. Sebastian Lobo-Guerrero for his excellent presentation. In fact, these micropiles are very, very effective. We also have seen on many sites, they work very well. And he has given a very good two examples where one can use where there is a distinct failure plane. One is means at the boundary of the two materials, that is rock and soil. And second example he has given from the soil mechanics, where there is a continuous loading on the micropile. So it is very, very excellent lecture. And on behalf of all of us from the IGS Roorkee chapter and from on behalf of all the attendees, I thank the speaker for his excellent lecture, and also uh, my congratulations to all my student group here, because this lecture is organized by our student chapter. That's a great activity they are doing. Thank you very much.
Thank you, sir, for your words. Now we have come to the end. I'd request Dr. Sebastian to say a few words. Like there were about 100 participants in the lecture which I saw. So I request him to say a few words. Then we can have a photo and then we can stop.
Yes, no, absolutely. I mean, I'm truly honored by this opportunity. You know, I hear this sentence somewhere, sometime, that says, "Attention is the most generous gift that anyone can give you," and I truly believe that. Right? I mean, there is a lot of things going on in the world these days, and you can spend your time in many things. Um, one thing is listening, but another one is attention. Right? Dedicating yourself to listen to somebody and try to understand what they are saying. It's a generous gift, and I'm extremely thankful for that. So I appreciate this. Obviously, to the organizer for having these events. I think it's great initiatives. You can count on me for anything like this. As I said, I have many presentations on many topics. If in the future at some point you want to cover another topic, always count me in. As a student, I never really have the chances to attend these things, and I think it's great that you do it. And the energy on all these events and the excitement and the interest on geotech is really what we need to make sure that the new generations continue the beautiful profession that we have. So this is a perfect way to start my Friday. It's funny because when I started, I was dark. You guys have light. Now I have all the sun in my head. You guys are dark in the day, but it's great that we have tools to do this together, and it was a very pleasant experience. So thank you very much.
Now I request all the participants to switch on their camera so that we can have a group photo. So I think the photo has been taken. So I thank you once again, sir, for accepting the request and giving the wonderful lecture. Hope to see you soon, sir.
Absolutely, and have a great weekend. Thank you very much. Looking
Same
forward
to
to
you, sir.
future collaborations.
Thank
Thank
you.
you.
Okay.
Thank you
Bye.
very much.
Yeah.
Thank you
Okay.
very much.
Thank you.
Thank you,
Bye.
sir.
Bye bye.